Hello again. What I want to talk about now is again on alkyl halides, and specifically how you can predict. I want to give you some strategies for predicting what the products will be in a reaction of an alkyl halide with either a nucleophile or a base. And I've said this before, but often the same chemical species might act as a nucleophile or might act as a base, depending on what the opportunities it sees in the organic molecule it attacks. I think I drew this one before too. This would be 2-bromo-3-methylpentane. And I'm saying what happens when a nucleophile or a base attacks this? Now there are a couple of questions. The thing you would love to be able to answer is what's the favored product? What's the most likely product? But also you'll need to know what other, at least consider what other kind of products might be formed. And then you think, well, what's the possible or even the probable mechanism of the reaction? So all of these things, what the reactions are, what the products are, and what the mechanism, this is the subject of our present work. Let's look at these things in reverse order. So once again, I'll just remind you, but by now I hope you know, that in an alkyl halide like that one, the whole reactivity derives from the polarity of the carbon to bromine bond, the carbon-halogen bond. The halogens are more electronegative, so the electron density is pulled away from the carbon. And even though we will never, or almost never, show these detail, you must understand that that's a polar bond, that carbon has some positive character and the bromine has some negative character. And furthermore, because the bromine has some negative character, it's a good leaving group. That means it's willing to grab the pair of electrons and split, go away from the organic framework, from the organic molecule. Now, I pointed this out, that Smith tends to judge the quality of a nucleophile, the nucleophilicity of a chemical species, or the basicity of a chemical species. That means the ability for the nucleophile to form a bond to a carbon. The basicity is how good is that at abstracting a proton, in our case, from a carbon atom. She says you can judge that, and you can also judge the quality of a halogen as a leaving group basically by its basicity. So you can use a table of acid strengths, or which is also the table of conjugate base strengths. These are different. A base specifically is defined as something that forms bond to a proton that may or may not, may have a bond to a proton, it might let go or it might not let go. That's its basicity. What we're looking at now are the ability of, for example, bromine to form a bond to a carbon, or the ability of a nucleophile to displace that, so the nucleophile would be forming a bond to a carbon and kicking that bromine out, or it's the ability of a base to pull a proton away from a carbon. She's not crazy, of course, but it's a bit of a stretch of the notion of basicity. But it's okay, we understand what she's doing. So again, I wrote these nucleophile anion or base anion as if they're different. They're not. Often the same chemical species might act as a nucleophile or might act as a base. And the reality is kind of simple. Often the role that a potential nucleophile or potential base plays depends upon its shape. Is it skinny or is it broad? And it also depends upon what its target is. Is the target accessible, such as that carbon might be a good target for a nucleophile? That carbon, the tertiary carbon, would not be such an attractive target for a nucleophile. And is the shape of the nucleophile or base, how is that? Is that good at getting into a tight place, or is it not? It just pluck away a proton from the periphery of the molecule. These things are actually kind of easy to predict, or at least to make a good guess. But again, I'm going to try to guide you in that right now, how to judge whether a particular chemical species will act as a nucleophile or as a base. It depends upon the conditions. The question of mechanisms, again, this is kind of new to you. It's the first time that the word mechanism, this chapter is the first time that we start talking about the mechanism, that is the step-by-step process of a chemical reaction, that we start to look at these and characterize them. Now, the mechanism of what happens largely depends upon the organic molecule. And I'll explain what that means, what I mean by that here. If nucleophile is going to act as a nucleophile, nucleophile will take its pair of electrons, attack a carbon that's got a good leaving group, and displace that good leaving group. The action is all displayed by those two curved arrows, and you will, I think you can now, predict that if those two blue arrows are the mechanism of the reaction, the product would be this. You'd have the same, I'm going to turn it upside down, but the same 5-carbon chain. The middle one has a methyl group, but now, because of the action, nucleophile is bonded, and bromide anion, I'll draw in all the electrons, bromide anion is displaced. If these two curved arrow actions happen simultaneously, that is in one step, the reaction is called a bimolecular reaction, an SN2 reaction, substitution nucleophilic bimolecular. Bimolecular, because that's an observation, an experimental observation, that the rate of the reaction, the rate at which that becomes that, depends upon two chemical species, the nucleophile and the alkyl halide. That's just something that one can measure experimentally. And from that, one infers that that must be the mechanism. They just bang into each other in one step and all the events happen. Now I'm going to propose that in the reaction of a strong nucleophile, I've mentioned to you a couple of times that methoxide is a perfectly good, strong nucleophile. It's got a negative charge, it's lean, knife-like, and this could happen. The methoxide would have no trouble really attacking the secondary carbon, secondary because that carbon is itself bonded to two other carbons, secondary carbon, and displacing the bromide. Those two curved arrows indicate a simultaneous event, what we call an SN2 reaction, nucleophilic substitution with two chemical species in the rate determining step. And if that happens, the product we get would be, but now we have a bond here to methoxide, and a bromide anion displaced, SN2. Now, I want you to consider, I'm just going to erase a couple of things, and I want you to consider, what if we were dealing with, not with a strong nucleophile like methoxide, but with a weak nucleophile?